welcome to this section of the course. In this section, we'll be turning two curves into one. So I'm very excited to show you this section because that's one of the purposes. I told you at the beginning of the course that when we have two curves here, in many engineering scenarios, you will have to find the result of adding two curves. There may be sound waves or any other ones, so that you turn them into one curve here. Okay, so I'm not going to explain applications of this theory, but it's quite helpful in engineering sciences. So let's get to it. So in this very first, this is one more time, showing curves with different amplitudes can be added together to give you either a sine curve or a cosine curve. Now, the amplitude of the resulting curve has a value of r, capital R, and there will be a phase change, which is given by alpha inside the bracket. So we're going to this value of capital R is, and what that phase change is, that value of alpha inside the bracket. The question will tell you whether they want it in the sine form or the cosine form. So there's no need to panic. We will be told either to give it in the sine form or cosine form, and we'll figure it out according to what the question asks us to do. So let's look at this first example. We have 3 sine x plus 4 cos x, and we want to express this we turn it into a single sine curve. Okay, with capital R being positive number and phase change we've been told needs to be between 0 and 90 degrees. So what do we do? Well, we know from what we learned earlier that uh, double angle formula, here we have an addition inside the bracket here. Okay, the result needs to be a positive alpha. So we are going to take the very top left corner. There is the formula for sine of alpha plus beta. We're going to apply that formula there. So how do we do that? We simply have the capital O multiplied by this. So we are simply multiplying up both of these terms, which come from the formula in the top left corner, and we just timesing them up by capital R. So nothing tricky about that for now. Alright, so then we're gonna look to match up some terms with each other. We have 3 sine x plus 4 cos, and that has to equal to this expression here. So we see that this sine x and sine x match up with each other, and this cos x and this cos x match up with each other. That means the remaining terms, the capital R times by cos alpha, is in fact 3. So those blue underlinings must equal to each other. And so we put that aside, and therefore we have this green underlinings that 4 must match up with R times sine alpha. So we write R sine alpha equals to 4. Okay, so where do we go from here? Fantastic. So we learned that from basic trigonometry, we can draw ourselves a little right angle triangle here, cos representing the adjacent over hypotenuse and sine representing the opposite over hypotenuse. We draw up ourselves angle alpha here, and the opposite side has to be a 4 over R, and the adjacent side is 3 over R. Where do we put capital R? Capital R goes for the hypotenuse of that triangle. Okay, so one of our purposes, we're one step closer to calculating this value of R, because on this right angle triangle, all we have to do is use the famous drum roll Pythagoras to figure out the answer for r. So we take a square root of 3 square plus 4 square. Now, we all know that the answer to that is 5. Now, there is a long-winded process. I rearranged this sign very quickly so that I divided both sides by r. So we'll have this expression and divide both sides by r to get this expression. Now 3 over r was cos, that's how I came up with that. You always end up with the same value of r in these two expressions, so you will use Pythagoras theorem. That's much easier. Now I can show you the long-winded process here is to square both sides here. R square cos square alpha equals to 9, and square both sides of this equation. R square sine alpha square equals to 16, and we can add this equation and factor a capital R out of both those two terms. So let's call this equation 2, and here I'm going to add equation 1 and 2 together, and we'll end up with cos square of alpha plus sine square of alpha inside the bracket here, equaling to 9 plus 16. So this expression is 1 cos square plus sine square, so r square will be 9 plus 16, and this drum roll will give us that square root of r is a square root of 25. Now, I think that drawing the right angle triangle is much easier than going through the algebraic working out, but it's up to you which route you want to take. I would take the drawing of the right angle triangle. Now, final step in our calculations is to figure out what the value of r is. There is different ways to do that. I could the tan of alpha to be equal to 4 over 3, but there is another way which we could use cos of, now that we know what the value of r is, we could take cos of alpha as it's on the PowerPoint here, take cos of alpha to be 3 over 5. Both of these expressions will give you the same answer. Taking inverse cos of 3 over 5 is the same as, give you the same answer as taking inverse tan of 4 over 3 opposite. So both of those answers will give you the same angle, alpha to be 53.1, which is automatically between 0 and 90 degrees. So let's look at the next example. Okay, so before we move on, we can nicely write up what the value of r and alpha is in this expression here before we move on, so that we get our full mark here. Okay. This example, we've been asked to once again use the first equation and write it in terms of a single sine curve, with alpha being between 0 and pi over 2, noticing that the angle here needs to be in radians. So make sure your calculator will be turned on into radian mode. Okay, so how do we deal with this expression? Previously, we had two terms here, but there is a term missing here. What could it be? Well, when we don't have a factor there, we can put it 1 there. Okay. This time we have subtraction inside the angle bracket. So we're gonna take the corner for sine and use that to our advantage here. We will simply multiply by capital R on both sides, so we get this expression, and we will use number 1 for what's missing there. Okay, so we said because this sine matches up with this sine x, and this cos x matches up with this cos x, the remaining terms that's underlined in blue will be equal to each other. So from that, r cos alpha is 1 and r sine alpha is root 3. Okay, so we draw ourselves a little right angle triangle here with angle alpha, and root 3 over is the sine value, 1 over r is the cosine value. We take the hypotenuse with Pythagoras calculator will tell us that square root of 1 plus root 3 squared will give us a 2 for capital R, and we can take no matter what you use now, you can use take inverse cos of 1 over 2, or you can take inverse tan of root 3 over 1, doesn't matter. You will get the same answer. So we substitute the value of r that we found in the previous part. So cos alpha is 1 over 2. You could read that off from this angle here. We say adjacent side over hypotenuse is 1 over 2. And you take inverse cos of 1 over 2, and you end up with pi over 3, making sure that our answer is within the range. Yes, pi over 3 is less than pi over 2, so we write it up neatly. We write 2 sine x minus pi over 3. So this expression is equals to 2 sine x minus pi over 3. Now, if you had to sketch the graph for that, as the part B of the book answers to do, that this vector is stretching the sine curve by vector of 2, so we'll have sine curve going from 2 to minus 2 if we had to sketch this graph of I'm sketching graph of sine x minus pi over 3. So this for now is just 2 sine x. Now when we add the phase shift of negative pi over 3, that will actually move the graph to the right by translation by pi over 3. So then we will move to the right. The x and y axis will actually go to the left side by a factor of pi over 3. So that means we will have this shape. This distance here will be pi over 3. Okay, so that means that now this point here will be pi over 3 and so on. Okay, so let's look at the next example. So in this example, we've been asked to express 2 cos theta plus 5 sine theta in terms of cos, and we have subtraction between these two angles. So alpha phase shift needs to be alpha needs positive value, but we will have a minus sign there. So we are going to appeal to this formula here. On top of the page, I'm circling cos alpha minus beta, and we will appeal to that. We're going to multiply everything on that line by capital R, so we get this expression here, and we're gonna do some matching up terms. So matching up the cos alpha with cos alpha with cos theta with cos theta, and sine theta with sine theta here will leave us with 2 equal to r cos alpha, and 5 will this blue underlinings must equal to each other, and these green underlinings must equal to each other. So 5 must equal to r times sine alpha, because, well, you can just move these factors around, and you get this expression here. Now that means sine alpha is 5 over r. That means opposite side of angle alpha is 5 and adjacent side to alpha is 2. We use Pythagoras to figure out what the length capital R is. Capital R is always the hypotenuse, so this case is root 29. We can use the same one of these expressions, doesn't matter which one, uh, to figure out what angle alpha is. We divide 2 by root 29 and then take inverse cos of 2 over root 29 to get the angle that we are required to find. We were required to find an angle in degree form, so this matches up. Make sure you calculate this in degree form when you calculate that. Finally, you write off your answer to be uh, what they are. We're going to replace r with root 29, this example, and write uh, negative, uh, well, rewriting of what the angle theta minus alpha should be. Okay, so let's look at the next example. Well, we asked to solve an equation. Solve an equation that's actually sine and cos in it. If you try to rearrange this equation, what you might initially think is that why not just divide sine by cos and use tan inverse? But I'm just gonna, as a devil's advocate, I'm gonna try and do this the wrong way to show you that it wouldn't work out that way. So if we took the sine to the other side and write minus sine minus 5 sine theta plus 3 there. This plus 3 here, we cannot, if we think by cos, we'll end up with a negative 5 sine theta, and we end up with 3 uh, here. This 3 divided by cos is nonsense. That doesn't help us get a tan that we wanted. Yes, this expression does give us tan here, but this nonsense here doesn't help us solve it. So let's look at the correct way to solve this kind of an equation. We're going to have to appeal to what we have learned with double angles here. Let's see if the questions doesn't actually tell us whether they want the answer using a capital or times cos or sine. So we can choose as we wish. We can take uh, the double angle with the sine formula, for example. Actually, uh, my bad. What we figured out in the uh, previous part of this question was that uh, these two are equivalent to each other. So we did drive this derivation. I did show you the derivation of this equality. So rather than solving plus 5 sine theta, that uh, that doesn't help us, but the right side of this equality does help us. We can set root 29 cos theta minus 868 to equal to 3 and solve this equation. How? Yeah, simple. So we can divide, because there is only a single trigonometric function here. We divide both sides by root 29 and okay, so that's just showing that those two are equal to each other. There is a phase change here, so we do adjust the range to be between negative 68 and 291. So then that's simple. So dividing by root 29 and taking its cos will give us this equation here, which the initial value is 56.1. Now, because we took cos inverse, the cos inverse means that theta equals to 360 minus theta. So whenever you use cos, uh, well, the cos of this angle is equals to cos of this angle. But you get my point is that the other alternative angle is 360 minus 56.1. So we will have 303.9, I guess. So there is okay. So that actually, yeah, that answer is beyond the range that we want. 300. Yeah, this answer is beyond the range that we need. That goes to 305 or something. So that's bigger than this value here. So we actually go and take the negative version. If we just use the fact that cos is an even function, cos of theta equals to cos of negative theta, then we're going to take minus 56.1 to be the other answer there. Now, then the final step is to add 68.2 to both sides of the equation. So that answers 303.9. We have to chuck away. Okay, so the final expression will tell us that the answers will be 12.1 and 124.3. Okay, so this is a different example, and we've been asked to calculate maximum value of this expression here. What is the and the smallest positive value for theta that will give us the maximum. So it doesn't matter whether you go for sine or cos, we have an addition between these two terms. We That means that we either have to use this expression or this expression here. Either one of these two would work, but we have gone for this cos. So multiplying both left and right of that expression by capital R will give us this. As always, in like previous examples, we underline the matching terms. So these are cos theta and cos theta match up with each other. Sine theta and match up with each other. That means the remaining parts, the blue underlinings must match up and the green underlining must match up. Then we put these values on a right angle triangle. The opposite side must be 5, the adjacent side must be 12. This is a famous Pythagorean triplet, so we get capital R to be 13 and take either of these expressions, either R cos alpha or sine alpha, substitute the value of 13 into it to solve for alpha. Okay, so solving for alpha, we are going to end up with 22.6. Okay, so how do we answer the question as they asked us to do? We can rewrite this expression as 13 times cos alpha minus 22.6. And when will we get the maximum for this curve? Well, uh, what is the maximum for this curve? Cos of any curve will oscillate between 1 and minus 1. So the maximum and minimum of the original cos curve is plus 1 and minus 1. But when we multiply by a factor of 13 here, the scale factor here changes the amplitude to positive 13, negative 13. We're looking for a maximum, so by maximum they mean what's the y value there. So the maximum y value is 13. Now at what angle, what's the smallest angle that it will appear at? What is this angle going to be? Well, I've drawn you by mistake. That's the sine curve. The y-axis would be here for cosine curve, right? Okay. So what is the phase? The cosine will have its maximum at 0 degrees. So what value of theta will equate this bracket, the angle bracket, to equal to 0? Basically, we have to solve this problem, to solve this equation. theta minus 22.6 must equal to 0 because uh, 0 degrees is where the, the maximum occurs. Solving this equation for theta will have to be 22.6 degrees. So the smallest angle that will give us uh, the maximum is when theta is 22.6. So that's the answer to this final example. So I'll see you in the next video.